This year, we're also starting something new with the Levchin Prize. In fact, the steering committee invites one of the Levchin Prize winners to deliver the Levchin Lecture. And so this year, we chose Adi Shamir to deliver the first inaugural Levchin Lecture. And Adi is going to talk about how to securely implement cryptography in deep neural nets. So Adi, the floor is yours.
So I'm going to talk about a new topic. This is very recent result. It hadn't appeared so far in any conference, but you can find it in ePrint. And it's joint work with two colleagues from Technology Innovation Institute from Abu Dhabi and Eyal Ronen from Tel Aviv University. So there are two huge areas of research. One of them is cryptography, security. The other one is AI. Both of them are very active, lots of interesting results. But in the past, the intersection between them had been quite small. I'm not talking about how to use AI in cybersecurity. This had been an active research area. But cryptography per se had almost no intersection with AI. And actually, when I decided about 3 or 4 years ago to move into this area, the reaction I got when I submitted papers to Crypto and Eurocrypt and Asia Crypt conferences often included a remark by the referees that why does this topic belong to cryptography? And on the other hand, after publishing several papers and after others got into the field, my latest published paper, which is going to be presented at Eurocrypt 25, actually won the Best Paper Award. So you can see that there is a total shift, and now people are accepting questions of security in artificial intelligence as being a major part of the crypto tool set. So today I'm going to talk about a topic which is right at the bullseye center of the intersection between the two areas. And this is the question of, okay, we have all kinds of cryptographic schemes. Can we implement them in a secure way in a deep neural network? So the problem is that cryptography is essentially digital, and it maps bit strings to bit strings. On the other hand, deep neural network is essentially analog, and it is mapping real valued inputs into real valued outputs. And it's essential for deep neural network to be continuous, because without the continuity, you cannot do gradient descent, you cannot calculate the gradients, et cetera, et cetera. So there seems to be a gap. They are incompatible. The discrete questions dealt with by cryptography and the continuous world of deep neural networks. I want to mention that for about 2,000 years, we had been using analog computers, starting with the Antikythera mechanism for navigation used by the Greeks. We have been using for several hundred years the slide rule in order to solve differential equations. Bomb sight, Northern bomb sight in Second World War was an analog computer. But about 70 years ago, everything changed. We dropped all the analog computers. We started using only the Colossus code-breaking machine in order to break crypto systems. IBM introduced the mainframes. We have microprocessors, and all the analog computers were thrown to the sideways. On the other hand, I claim that in the last 20 years, there is a shift back. And the way I interpret MAGA is make analog great again. Because if you think about quantum computers, we are talking about zeros and ones as states, but the actual qubits contain a continuously varying kind of combination, linear combination with coefficients which are complex numbers. So there is something continuous. And if you think about how Grover's algorithm, for example, works, you have a vector in Hilbert space, and you continuously shift it until it moves into the right direction. So there is a lot of analog elements in quantum computers. Of course, all the deep neural networks are analog because they are mapping real values to real values. And there are all kinds of new technologies, neuromorphic computers and other models, which are also using analog ideas. The fact that even digital devices have an analog characteristic had been known for a while, at least since Kocher had demonstrated how to use side channel attacks, because if you are looking at a microprocessor, there is a continuously denominated emanations from it, how much power it consumes, what kind of electromagnetic radiation it creates, etc. These are analog outputs coming out of a digital device. When you are doing cryptanalysis by analyzing power traces, again, you are looking at the analog shape of those curves. When you are introducing fault attacks, you are creating all kinds of jitters in the timing of the clock or using unusual input voltages, etc. And this creates just a one-time kind of glitch in the operation of the device, and then you are able to break the crypto system using the analog outputs of a digital device. So if I'm trying to summarize the situation, there are users at the top, and there are adversaries on the left-hand side. So the users usually have digital data that they want to encrypt or to do other cryptographic operations on, and they can use digital data on a digital computer, or they can use digital data, but they're using a leaky computer. It's a digital computer with analog characteristics. And then there is the digital data, which is implemented on an officially analog computer, not one which unintentionally emits some analog signals. Now, the adversaries can try to use digital attacks. So the combination of digital attackers and digital computers leads to standard cryptography that we are all interested in. But there are actually users who are using digital data and leaky digital computer, and they are using analog attacks, and this leads to the side channel attacks. And there were some papers which tried to look at the issue of how do you implement cryptography on a totally analog computer, like a deep neural network. There was a famous paper by Shafi Goldwasser and Vinod and Zamir and several other researchers. But they said that even though they implement their cryptography on an analog computer, such as a deep neural network, the adversaries are only allowed to use a digital attack. And they missed all the fun, because I claim that the interesting results happen in this corner when you are actually allowing the users to implement cryptography on an officially analog computer, and the adversaries are also allowed to use the analog attacks. So now that I've placed the paper I'm going to talk about in context, let's define what does it mean, what is the deep neural network that I'm usually looking at. You have many layers. In each layer, you have a linear combination with real-valued coefficients of the real-valued inputs coming from the previous layer. And after you perform this linear mixing, you apply a ReLU function, almost always the ReLU, which is a continuous function, 0 for negative inputs and copying the input to the output for positive inputs. And because linear mappings are continuous and the ReLU is continuous, if I'm taking the inputs and I'm moving them up and down in a continuous way, the outputs are also going to move down and up and sideways, etc., in a continuous way. There are no jumps anywhere when you're implementing cryptography on an analog computer. Okay, so let's get to the issue of how can I implement crypto systems such as AES, which will be our running example, on an analog computer like a deep neural network. I want it to be correct in the sense that for every combinations of 0, 1 as real valued inputs, I'm going to get the correct 0, 1s in the output. And it turns out that deep neural networks are universal. They are powerful enough to be able to implement any digital mapping like this. But along the way, unintentionally, they also create outputs for inputs which are strange, which are not zeros and ones due to the continuity. So DNNs are both digitally universal because they can implement and, or, and not very easily. You can write very simple DNNs which do it. And then by composition, you get any Boolean circuit. And they're also analogly universal because there are results about how you can approximate any continuous real-valued function with a wide enough deep neural network. Okay. This is now a new playground with new rules, new techniques, because the attacker can now ask the deep neural network on which the cryptography is implemented, please tell me what is the result of encrypting a plain text whose first bit is 0.3, somewhere in between 0 and 1. The second bit is even outside the range of 0, 1, so -7. The third bit is 3.1415, etc. And it will give you an answer. Now the question is, will this answer leak any information about the secret key or not? Question that no one had answered before. Another example, an attacker can apply what we call a jitter attack, in which you take one of the bits in quotation marks because it's a real number, and I can slightly shift it forward and backwards and see what kind of effect it creates on the real valued outputs. Something which is unimaginable in the binary case. A third example, the attacker can move from one plain text along a straight line to another plain text and see the piecewise linear kind of behavior of the output as you move from one plain text to the other, whereas when you deal with binary input, I can only jump from this input to that input. So I hope it's clear why the game is completely different. And I just want to mention how keys are handled. I assume that the attacker has access to a black box. He doesn't see what's inside. There is input coming from the outside for the plain text. There is an internal register which contains the key as zeros and ones. This cannot be seen and cannot be manipulated. I'm not talking about related key attacks. So this is fixed inside. And then you get real valued outputs coming out here. Okay, so you cannot see the top of my slides, but the question is, how can you implement cryptography on the DNN? And I give the example of AES. So everything in AES can be implemented by just two types of elementary operations. One of them is a mapping of 8 bits to 8 bits. These are the S boxes or the multiplication by the constants 2 and 3 in the finite field of the AES linear mapping, or mapping 2-bit inputs to 1-bit output. And these are the XORs, where you XOR a subkey or you XOR 2 bytes when you are doing the linear mixings. So if I can implement these two operations, I can get a complete, very simple kind of implementation of AES as a deep neural network. So there is a very natural and simple way how to implement any Boolean function with a small number of inputs as a ReLU-based DNN. And this is described by the notion of corner functions. So a corner function, think about the Boolean cube. Suppose it's the 8-dimensional Boolean cube. It's supposed to describe how 1 bit of the output is mapped by the S box from 8 bits of inputs. So it's eight-dimensional Boolean cube, and each corner has zeros and ones written on them. I'm going to concentrate on a single one in one of the corners, and I can use a ReLU whose zero, the zero value of the input, the region in the eight-dimensional input space, which gives a zero as an input to the ReLU, is kind of diagonally oriented hyperplane. And now everything which is on the far side in the direction of Dan is going to give negative input to the ReLU. So it's going to give a value of 0. And as you are moving in the direction of the corner with the 1, it starts from the value of 0 and it increases until it reaches a value of 1 at the corner. So if I think about this corner function, it is going to give me 1 at the correct corner and 0 everywhere else. And now if I want to implement a Boolean function which has 128 ones, in AES, for example, each bit of the output of an S box is balanced, has 128 zeros, 128 ones, I just add together 128 corner functions, where each corner function corresponds to a corner with a 1 in it, okay? So the particular corner function here, with the three-dimensional example, is ReLU of x1 minus x2 plus x3 minus 1, and this is going to be 1 only at 1, 0, 1, and 0 anywhere else. And if you sum them up, I will describe all the corners which should be 1. So I hope it's clear what a corner function is, and this enables me to build the 2 to 1 or the 8 to 8 functions that I need in order to implement AES. Okay, so already explained this. How do we implement the XOR? It's a special case, two-dimensional special case of the general small number of input corner functions. So you can easily implement XOR by ReLU of x1 minus x2 plus ReLU of x2 minus x1. If you think about it, this is just the absolute value of x1 minus x2, which gives me 0 if they are equal and 1 if they are unequal. Okay, so this is how I'm going to implement. And we call this idea of using corner function the natural implementation of AES as a DNN. And it is correct because for 0, 1 inputs, it gives me the correct outputs. And now the big question is this natural implementation secure when an adversary can use real valued inputs? Now, there is an interesting result in the paper you'll find on ePrint, which I don't have time to present, and this is a very unusual case where I have an exponential separation between the real valued complexity and the Boolean complexity. So I can show a very simple function which can be implemented with one neuron, single ReLU, so that if you are only allowed to ask questions which are zeros and ones, it will probably take exponential time to solve. Well, if I can use real valued questions, I can solve it in linear time. So look for the details. So the answer is that just as a text, side channel attacks become very easy, all these natural implementations of cryptography can actually be easily broken. And the reason is that almost any secret key block cipher, including AES, starts by XORing each input bit to a key bit. And I'll start by concentrating on this initial XOR and show how to extract the key bit that had been XORed to the plaintext bit. And we'll use a jitter attack, which just tries to move a little bit the input and see what is the effect on the output. So here is the Boolean function of the XOR. I had the plaintext bit, which could be 0 or 1, and I have an unknown key bit, which is 0 or 1. And the XOR, the output of the XOR is 0 here, 1 here, and 1 here. And now think about implementing it with corner functions. And let's first assume that the two ReLUs are kind of separated from each other. So I have a region here which is totally 0. Here it goes up towards 1 at this corner, and here it goes up towards 1 in this. And now, where am I? I know the plaintext bit, it's 0. So I know that I'm either in the first floor or in the second floor, but I don't know which case. If I'm jittering, I'm moving left and right here, I'm in the 0 region, and therefore, the output of this initial XOR will not change as I'm jittering left and right. If the only change I make is in this one plaintext bit, it is immediately XORed, and the result is being used elsewhere. Nothing changes in any of the bits which are getting into the later stages of the encryption, and therefore the ciphertext, the outputs as real values, are not going to jitter. They're going to be stable because I lost the jittering at the very first step. Whereas if I am in the second floor, I'm in a region where moving left and right does change the value of the XOR with respect to this diagonal. And therefore, I have a very simple jittering attack which will recover all the first subkey. But this worked when the two XORs are not back-to-back as they were. If you remember, I said that I'm looking at ReLU of x1 minus x2 plus ReLU of x2 minus x1. And there, if you think about it, the two 0 are the same diagonal. So what happens if I'm in this case? I have back-to-back ReLUs. I can still solve it because if I'm moving in this direction, the value goes up from 0 towards 1. So I'm moving in epsilon up. And if I'm jittering in the other direction, it is also going up because you had a kind of V shape in the output. And therefore, at plus epsilon and minus epsilon in this plaintext bit and no changes in the other plaintext bit, I get the same output coming out. Whereas here, if I jittered in the positive direction, I'm going to have one value. And if I'm jittering in the other direction, I'm going to get a higher value coming out of the XOR. And this is going to avalanche and affect everything else. And I'm going to see a totally different ciphertext. So I can distinguish between the case in which jittering up and down will give me the same ciphertext or different ciphertext. And this will tell me whether I'm in the lower floor or upper floor, and it will leak out the value of the key. So I hope this was clear. But there is a very easy way how to solve it. And this is if you are not allowing values to be lower than 0 or higher than 1. I'll show you in the next slide a very easy way, how we call it sanitization. I can easily restrict the inputs to be in that range 0 to 1. And then I can jitter only in the positive direction here and the positive direction here, increasing the value from 0, etc. And then this is increasing the value coming out, and this is increasing the value coming out. So the ciphertexts are, in both cases, going to be different. So I'm not going to see whether I'm at the bottom layer or the top layer. But this can also be solved with a more complicated solution. So we don't have perfect sanitization. I don't have any function which can be implemented on a deep neural network, which will give me, for example, the value 0 if the input was up to 1/2, and 1 if it was 1/2 or higher, because this is discontinuous, so I cannot implement it in a deep neural network. But I can do the next best thing, which is partial sanitization. This is going to give me a value of 0 if I'm giving any negative input. It is going to grow linearly until I get to the value 1, and it will stop growing after 1. And this is actually going to chop my jitter attack. I cannot go to negative values below 0 or to positive values above 1. OK, this is implemented very easily, like ReLU of x minus ReLU of x minus 1. It gives you exactly this behavior. So we have another attack. Since I'm starting to run a bit out of time, I'll not give you the idea. So I cannot concentrate on the XOR, but I can concentrate on the first S box after that XOR. And I can identify a very special behavior if the input to the S box was 0, sorry, if the output of the S box was 0, 0, 0, 0, 0, 0, 0, 0. 8 zeros at the output of the S box are going to behave differently with respect to jitter attacks than all other 255 inputs. And the reason is a bit more complicated, but you can easily find it. So I'm not going to find the key by looking at the initial XOR, but I'll find the key by looking at what happens the next step afterwards when I go through the S box. Okay, so I'll skip the explanation of this. And now we come to the last part of my talk, where I'm going to answer the question, can you implement cryptography in a secure way on a deep neural network in a way which will not be easily breakable like all the attacks I showed you so far? And we know from experience with side channel attacks that it's very difficult to solve all possible types of side channel attacks. And here the attacker has even more powerful tools available to him. So at first we were quite skeptical that there will be any secure way how to implement it. But then after thinking hard, we actually found a provably secure way to implement any cryptographic functionality in a ReLU-based DNN. And I'm going to give you the basic ideas now. So first of all, I'm going to change the sanitization function, make it a bit narrower. I need some playground near the 0 and near the 1. So I'll do the sanitization so that it will, for any value below 0.1/3, I'm going to give an output of 0. And then it will go up more steeply, up to 2/3. And then any value of the input, which is more than 2/3, I'll output a 1. This is going to be applied to the inputs or to any plain text bit. When you get an input value, real value, you first of all apply this one, and this can be implemented easily by difference of two values. Next, I'm going to think about what is the region which is still dangerous. So I've already made sure that any combination of inputs, with the exception of values between 1/3 and 2/3, is okay, because I've changed the input to zeros or to ones, and then I'm back to the analog, to the binary case, and I have guarantees there. So the dangerous part is if any one of the inputs is between 1/3 and 2/3, and this is a structure which I call the multi-wall. The multi-wall in each direction is going from 1/3 to 2/3, and if I'm anywhere outside of this multi-wall, I'm safe. The values, the input after the sanitization are going to be stable at 0 and 1s. No other values are possible. So the only dangerous region is in the multi-wall. And now I'm going to use another kind of function which will guarantee that the outputs for any point inside the multi-wall is going to be 0, 0, 0, 0. The ciphertext is 0, and therefore it will not leak any information about the plain text. But I'm restricted because I have to, for 0, 1, 1, 0, etc. plain text, I have to give 0, 0, 0, 1, 1, 0, 0, etc. ciphertext, and I have to change continuously. But the multi-wall is separating the input space into a multi-wall where the outputs will be 0, and into ortants, which are separated from each other. There are 2 to the n ortants. Within each ortant, I have only one point, which is Boolean. And the value in the whole ortant, for example, the one facing you, is going to be determined by a very easy smoothing formula from the one value at the binary point contained in the ortant. So I'm going to have the correct value at the ortant, and then it will just connect smoothly to the 0 on the surface of the multi-wall. It's a bit complicated, but think about it. So this smooth interpolation will not leak any information about the key, because anyone who knows, who is given an input, can calculate what the output should be for that input if he knows what is the result of encrypting a binary input into a binary output by AES. So I've reduced any analog attack into the digital attack. So here is the, we have to use some additional filter functions. We have something which is called rectangle, and then we have mask, which is the sum of rectangles. And this is our secure implementation. I'm taking the plain text, I'm applying input sanitization to each one of them, which will make only the multi-wall the danger zone. Then I'll use any DNN, even insecure implementation, like the natural implementation I mentioned to you. I take the output, every bit of the output is again sanitized into the narrow region of 1/3 to 2/3. In addition, I'm calculating the other mask based on the inputs. And finally, I have a masking layer at the output, which calculates ReLU of the original output after sanitization minus the mask. And for a reason that I'm running out of time in order to explain, you can show that this is provably secure in the sense that any attack, any analog attack on this particular implementation is not going to reveal any information about the key, which cannot also be obtained by being able only to ask binary questions and obtaining the binary output from a normal implementation of AES. Okay, so I'll just finish now. So the extra cost of the implementation, even though it looked a bit complicated, is trivial. It adds a constant number of additional layers, only 2 additional layers, and a linear number of additional ReLU-based neurons. And therefore, it is very easy to apply whenever you have to implement cryptography on a deep neural network, and it's completely practical. Conclusions. I think that this talk should open a new field of research about what does it mean to take a cryptographic functionality, which is only defined for zeros and ones, and apply it in a world where both the user and the attacker are allowed to use intermediate values or values which are outside the range. And we have a new tool set that deals with it. I defined the notion of natural implementation of schemes using corner functions. I demonstrated the insecurity of all the natural implementations. And finally, I described a different non-natural implementation, which is provably secure. Thank you very much.
Great, maybe we can take 1 or 2 questions. Actually, while people walk up to the mic, maybe I'll ask, so you described how this applies to symmetric ciphers. Do you think you can implement public key algorithms?
Okay, so in our paper, we describe, for example, what happens in signature verification algorithms. So in signature verification, the problem is not divulging information about the key because it's a public key. The problem is different. You have an algorithm for verifying a signature, which is giving 1 if the signature is correct and 0 if it's incorrect. Now, maybe someone will find a message in the signature where the signature is 0.2, 5.3, etc., which when applied, when computed by the signature verification algorithm implemented on the DNN, it will output 1. So we can actually show that our techniques can also solve this. Incidentally, it prevents you from having any input, any signature, which when evaluated will give you a value smaller than 1. And if there is another value, S prime, which is going to give you a value larger than 1, by continuity, there must be a point in between that is going to give you a value of 1. And therefore, clearly, if you have an implementation of a signature, where for some signature it will give you value smaller than 1, for other input it will give you value larger than 1, I can cheat. So there are all kinds of interesting questions there. Yes.
Oh, thank you. My question is, so your fix to the analog attack is also using an analog computer, right? So you're using
The same
real
technology.
values. What if that is now implemented using floating point on a digital computer? Like, do you see a problem there with the fix being not analog anymore?
No, I don't see any problem, but I assume that you have the ReLU because in order to implement In my solution, I was using sanitization, which was a ReLU, etc. So I assume that you'll have linear combinations and ReLUs implemented on a digital computer with floating point arithmetic. It will work exactly the same as a real analog computer.
Okay, thank you.
Thanks for a very interesting talk. I had a question regarding, do you have any idea on the computational efficiency if you implement cryptography into a deep neural network?
Okay, so let's do the analysis. In order to implement one S-box, each one of the 8 bits of the S-box required 128 corner functions. A corner function is a single ReLU. So I need, for one output bit from the S-box layer, I need 128. There are 128 outputs, so it's 128 squared. So it's 2 to the 14, 16,000. And you have 10 layers, so it's 160,000 neurons. It's considered a fairly small network. We actually implemented it, I forgot to mention. All our attacks were implemented and ran with 100% success rate on a PC.
Thank you.
Thank you, Adi. I'm going to go out on a limb here. Do you think that this is somehow related to the hardness of integer programming versus linear programming?
Whenever you move from the domain of integers to the domain of real values, the world becomes completely different. I can give you many examples. Linear programming versus integer programming is only one of them, but there are many additional examples where moving from one domain to the other makes the problem either much easier or much harder. So it's part of the same phenomenon that whenever you do domain extension, you have to reanalyze what's going on.
Okay, one last question, and then we'll break.
This will be a quick one. Thank you. This is a really cool talk. I'm very, very excited for the paper to come out. I'm definitely going to read it.
But the paper is an e-print, right?
The paper is in e-print.
Oh, okay.
We uploaded it a few weeks ago.
Oh, nice. I just wanted to ask a very, very silly question. Oh, well, I don't know. Just why would you want to run AES in a DNN? Where's this field going, do you think? Why would you do this?
Very good question. And the answer is that I can see many situations in the future where the DNN will be the main thing on which we are going to work. LLMs are implemented as DNNs. All the agents, new agents are implemented. Some of them are open source. You can download them, are implemented as deep neural networks. Now, why would you want to use cryptography? Because you may want, for example, to encrypt the input. You may want to verify that the input was given by an authenticated, from an authenticated source. You may want to, if you are trying to apply an instruction, you have DNN implementing an agent which has the capability to erase all files from your computer. Maybe you want to authenticate that this is indeed a legitimate instruction rather than something that a hacker gave in order to eliminate all files from your computer. So I can see many situations in which if you are given DNN, now you can implement in a secure way all the cryptographic functions directly on the DNN without having to go to another model of computation, get the result, and then give it again to the DNN. Thank you.